that introduction is sufficient. We are very happy that Professor Taboada agreed to give this colloquium for us. It is quite late at his place. It is 11:30 p.m. But irrespective of time, he agreed that he will tell us about this exciting discovery of NGC 1068 at IceCube and how over the last 1 decade, IceCube unfolded this era of high energy neutrino astronomy. So I would like to request Professor Ignacio that please tell us the excitement that we are having with IceCube.
Thank you very much. This is a very kind invitation, and thank you very much for the introduction. So I will tell you about a couple recent results by IceCube, and I will hope convince you that we're witnessing the birth of high energy neutrino astrophysics, and it will be up to you at the end to judge if this is really happening, but hopefully I can convince you. So since I need to talk about a bunch of topics, then I have an outline here on what I want to discuss. What are neutrinos and why is neutrino astronomy interesting? Then what is IceCube and how is that we detect neutrinos with IceCube? Then I will tell you an observation that was done starting about 10 years ago with an all-sky astrophysical flux of neutrinos, and then a couple of recent observations, NGC 1068 notably, but then I will also tell you about a recent gamma ray burst, and I'll finish up with a brief discussion of what I hope is the future for IceCube. So let me begin with neutrinos. Neutrinos are elementary particles, and as you know, matter is made out of quarks and made out of leptons. Quarks interact strongly electromagnetically and weakly. Leptons interact electromagnetically or weakly only. And see that the neutrinos are there. There are 3 flavors: the electroneutrino, mu-neutrino, tau neutrino. And because neutrinos are neutral, they cannot interact electromagnetically, so they can only interact weakly. And here you have the gauge bosons, and here you have the Higgs. And how strong is the interaction of neutrinos with matter is energy dependent. So I'm going to give you one example. It gets a little bit easier at the energies that IceCube works on. But if you look at solar neutrinos have energies that are about 10 to the 6 electron volts or 1 mega electron volt. And the mean free path of neutrinos made in the sun is about 1 light year in lead. That's how weakly interacting neutrinos are. And as I said, it gets easier at the energies that IceCube works at, but it is still extremely weakly interacting. Since I'm going to be talking about energy scales a lot as well, then I think it's good to put that in perspective too. In the upper part, you have electromagnetic spectrum with a visible range that is about 1 electron volt, ultraviolet, X-rays, gamma rays, and I have put here a handful of instruments that are able to detect X-rays and gamma rays. If you don't know these instruments, this is perfectly fine. But if you know them, that this puts you in perspective what is the energy range in which they operate. And then here, down here, you have neutrinos, and each one of these orange boxes is a source of neutrinos that we have detected already. For example, the Earth is full of radioactive materials that are product of the decay of uranium or thorium or potassium 40 and all the subsequent decays. And there's a lot of beta decays, and in beta decays you always get neutrinos out, and these neutrinos from the core, from the crust of the planet and from the mantle of the planet have been detected. Nuclear reactors are very copious sources of neutrinos. In fact, that's how the neutrino was observed for the very first time in the 1950s. There's the sun that via fusion produces neutrinos, and that of course has also been observed. This says supernovae, but it should really be singular. It should be one supernova in 1987, from which between 3 detectors, about 20 neutrinos in total were observed. You see that all these reactions, all these observations, I'm sorry, are sort of like the MeV scale, or 10 to the 6 electron volt scale. That is sort of like the nuclear scale. So it sort of makes sense that this is typical for these energy ranges. However, I'm going to be concentrated on IceCube, that is at much higher energies. You see that it's 6 orders of magnitude roughly above the nuclear scale. And TeV and higher, or 10 to the 12 electron volts and higher, is the energy that I'm going to be concentrated on. And atmospheric neutrinos that I will describe later, and astrophysical neutrinos are the 2 most important, or the 2 only sources of neutrinos that IceCube has observed to date. So why do neutrino astronomy at all? So there are several ways to answer that question. The simplest is that you have a new messenger, and that new messenger is going to provide you a new way of looking at things, and therefore you're going to be able to learn things that you cannot learn with the other method. There's a long history in astronomy of that happening. You can study an object in radio, and you can study it in ultraviolet, and you learn different things by looking at it in radio or in ultraviolet. So you're adding yet another messenger, in this case not electromagnetic, and you learn something. But let me put a very specific example. We know that the universe is filled with cosmic rays, and cosmic rays are high energy charged particles, for example, protons, or fully ionized helium nuclei, and so on. And we know that they're accelerated to extremely high energies that go all the way to 10 to the 20 electron volts, which is the same thing as 10 joules. And it is not possible to do astronomy with these cosmic rays because they propagate in galactic or intergalactic magnetic fields, and therefore their curvatures prevents the curvature of these trajectories prevent us from saying where these cosmic rays come from. Whatever you have, cosmic ray productions, these cosmic rays are going to interact with nearby material, or they're going to interact with nearby photon fields. And these collisions, and I'm putting here only protons, but it could be other nuclei, okay? These collisions are going to result in the production of pions. Neutral pions decay in photons, charged pions decay into neutrinos, and both photons and neutrinos travel in a straight line. So in principle, observing neutrinos is harder than gamma rays, so why not use gamma rays at all? And the point is that, and this is very interesting, is that the highest energies, the universe is actually opaque to photons. And this happens because if you have 2 photons that collide and their invariant mass is equal or higher to twice the mass of the electron, you can do electron-positron pair production, and you never observe that gamma ray. So you have these very high energy photons that interact with, for example, all the infrared light that fills the universe with the light from all the stars, or with the cosmic microwave background. And then these very high energy gamma rays, they interact with these very low energy photons, they get attenuated, they never get to Earth. So neutrinos are the only particle that travel in a straight line and can go from one side of the universe to the other at all energies that are interesting. So let me tell you a little bit about IceCube and how is that we detect neutrinos with IceCube. The basic detection method of IceCube is chunk of light. As an illustration, I have here the picture. This is a real picture. It looks a bit unusual, but it is a real picture of a nuclear reactor pond. So you have nuclear fuel that is inside of a large pool of water, and product of this radioactivity in the nuclear material, you have a lot of beta decays, and a lot of electrons or positrons are going to be coming out of these reactions very, very fast. These are going to be positrons or electrons that are traveling faster than the speed of light in water. Not faster than the speed of light in vacuum, that would be impossible, but it's perfectly possible that they travel faster than the speed of light in water. And whenever that happens, you produce chunk of light. And chunk of light peaks towards the ultraviolet and the blue, and that's why to our eyes this looks blue. And this picture looks really, really bright, and that is the product of a lot of radioactive decays at a given time. In fact, a single particle produces only a very minute amount of chunk of light. So the Meggish detection method for IceCube is neutrinos that will interact with matter. They will produce a charged particle, and this charged particle will travel through glacial ice that is highly transparent, and we will see the chunk of light. This is IceCube. It is instrumented at the South Pole. It is actually a walking distance from the South Pole, about 1 kilometer. You see that this here is what we call the IceCube laboratory. This is the very first picture that I showed. It's actually a 2-story building, and it's a large building. And South Pole to scale will be about here when I'm putting the pointer. So what we have done is that we have opened these 86 holes that are marked here. And these holes are about 60 centimeters in diameter when they get opened, and they're 2.5 kilometers deep. See that the glacial ice goes down almost 3 kilometers to bedrock. And in this 2.5 kilometer hole, after you open it, you lower a cable with sensors, with optical sensors, and that are instrumented in the bottom kilometer of the cable. So you get cables that are instrumented over 1 kilometer, and you put these 86 holes covering an area of 1 square kilometer, so you get a cubic kilometer of instrumented ice, which is what gives the detector IceCube its name. And the Eiffel Tower, by the way, is here to scale. The reason we have built the detector at the South Pole is, one, because if there's a station at the South Pole, so there's already infrastructure like power, internet, and other things, but also because the ice in Antarctica is extremely, extremely clean. It is cleaner than any ice that you can find in any laboratory in the world. There are natural processes that make this ice extremely clear and extremely transparent. The absorption length of light in the range and the wavelength that we care about in IceCube, which is towards the blue, ranges somewhere between 100 and 200 meters. It is a natural medium, so the medium is not homogeneous. The properties vary with, for example, depth, but the absorption length varies between 100 and 200 meters. It is truly very, very transparent. So in total, we have in this cubic kilometer about 5,000 optical sensors. And of these over 5,000 optical sensors, we have more than 99% operational, even though they have been working in the ice for 12 years or longer. And we also operate the detector all the time. We have over 99% uptime with the detector. And in fact, we're sensitive to neutrinos from all possible directions. We cover the entire 4 pi steradian in the sky. But as I will describe in this presentation, even though we have 4 pi steradian sensitivity, the best possible sensitivity that we have is in the northern sky. Or at the South Pole, looking north, we look through the planet, which is very interesting in itself. This is the IceCube collaboration. We are 56 institutions, 14 countries, and over 350 authors, counting some of the people that are here in the audience right now. This is how we detect neutrinos. And I'm going to describe only the 2 main channels. We have additional channels, but let me describe only these 2. One is called tracks. The other is called cascades or showers. In the case of tracks, you have a mu neutrino. That mu neutrino interacts with a nucleon, a proton or a neutron, in the ice or in the bedrock right under the ice. And then product of that interaction, a muon is produced. There's more stuff that gets produced, but let's ignore these additional things. Let's concentrate only on the muon. And muons are very interesting because among charged particles, it is the only one that can travel a very long distance through matter before it stops. at the energies that are interesting for IceCube, these muons are able to travel several kilometers before they come to a stop. This event that we have here, this is an actual neutrino from the data of IceCube, and it's actually an event that we think is of astrophysical origin. In this case, the neutrino comes from the right, interacts somewhere here, and then you have a muon coming out. And you can tell that because each one of these dots is a sensor. Each one of the spheres is a sensor that has seen light. The amount of light is given to you by the size of the sphere, going from 1 photoelectron at the smallest spheres to hundreds of photoelectrons at the largest sphere. The scale is logarithmic for the size of the spheres. And then also the color of the spheres tell you the relative time of observation. So orange is early, green is late. So it means that you have a natural progression from right to left of the particle. You can clearly see that this is a detector that is traveling the detector horizontally. And these tracks, precisely because you have this long lever arm from this point to this point, then it's easy to tell the direction. And there's more information than the lever arm that we use, but anyway, we can tell the direction to roughly 0.5 degrees. 0.5 degrees is actually, in terms of astronomy, absolutely dreadful. Compare that to optical telescopes, in which you can tell the position of something to better than an arc second. And you can realize how 0.5 degrees is not particularly good. This is limited to some extent by physics, but you know, it makes our life difficult. If you want to know what a half a degree is, take your arm, put it out, and the thickness of your thumb is about 1 degree at arm length from your eyes. So it's about half of that will be half a degree. And think about how many galaxies there are behind that half a degree. It will be impossible to tell from which specific galaxy one neutrino is coming from with only half a degree of uncertainty. Now, this is our best channel for telling directions. Showers, on the other hand, are our best channel for telling energy. And in the case of showers or cascades, you can have a neutrino of any flavor that interacts in the ice and produces a particle that is not a muon, is any other particle, absolutely any other particle that gets produced, is going to travel only about this distance, 40 centimeters from where it was produced. And then when it interacts, it's going to produce a couple new particles that will only travel a short distance. And each one will produce it will reinteract after a very short distance. And you get this cascading effect. You get this geometric increase in the number of particles until all of the energy has been deposited in a very small volume. It's going to be a volume that is going to be point-like compared to a kilometer scale detector. In that case, the amount of light that gets produced looks more spherical, so there's no lever arm, and that's why the angular resolution is significantly worse. It's from 3 to 15 degrees energy dependent, but the deposited energy is very well correlated with the neutrino. See that in this case, the muon can escape with some of the energy that is not included. And also this interaction for the tracks doesn't have to happen here. It can happen outside the detector, and the muon arrives into the detector also with some unknown energy that you couldn't observe. So this is really good for tracks, measuring direction, and these cascades are really good for measuring energy. They're complementary.
Ignacio, in your previous
yes, please.
slide, so in your previous slide, you mentioned about the left-hand side, the track. So these colors are the timing, right? And,
correct.
And the size of the spheres are amount of photoelectron deposited.
Correct.
Now, if I see some green patches at the beginning, these are green or not? Like
no, here the beginning is orange.
All
here
orange,
the beginning
right?
of orange, and the end is green. So it goes from right to left is how the event goes.
But
and
here
if you
on
look
the right,
here,
the timing information is lost. Like time is everywhere, right? Like, you know, because
so see that it begins in sort of like red orange here in the center. That's where it begins. And see that light propagates outward like a sphere. And that's why you have the green on the outskirts.
I see. Okay.
So it's like a spherical propagation of light.
Yeah. Okay, good. Thank you.
So let me tell you a little bit about the both signals and backgrounds in neutrino astronomy. And what I'm going to describe is the traditional way of doing neutrino astronomy. This is a method that was proposed in the mid-1960s. This is actually when neutrino telescopes like IceCube were first proposed. They were proposed not in the bottom of the glacier in Antarctica, but at the bottom of the ocean, but the idea is the same. And the idea is that you have very large number of cosmic ray muons that are observed in IceCube. In the case of IceCube, it's about 10 to the 11 muons per year. That's about 3,000 per second. And what happens is that you have a cosmic ray, again, which is a proton, helium, other nuclei. They arrive at the atmosphere, and then 20 kilometers high or so, they collide with an oxygen or with a nitrogen, and then a large number of particles is produced. It's called an air shower. And among those particles, you have muons. And muons, again, I told you that they can go through several kilometers at the energies that we can go about. So even though IceCube has 1.5 kilometers of ice on top of it to shield it a little bit, many muons can still all the way through, can still get all the way through and trigger the detector. So we have 10 to the 11 muons per year. In these very same air showers, you also produce neutrinos, which are called now atmospheric neutrinos, very naturally. These atmospheric neutrinos, because of the weak interaction, they can go from one side of the planet to the other, no problem. Sometimes the handful will interact near the detector, produce a particle that results in a track or shower that we can observe. And we can identify about 10 to the 5 atmospheric neutrinos per year. And only, I'm sorry, only about 400 of the events that we observe every year are actually astrophysical in origin. So you have a data reduction of 10 to the 9 to go from the particles that we observe to the astrophysical neutrinos. So it's a really very interesting statistical problem and computational problem. Now, the easiest tool that we have is to use the planet as a filter, because you see muons can go a few kilometers through through material, but they cannot go from one side of the planet to the other. So if you look for particles that are coming from below, if you're looking for particles that are coming from the planet, the only particle that we know that can do that is the neutrino. So if you look, for example, for an upward going muon was produced by a neutrino that interacted with matter just below the detector or a little bit below the detector. So the traditional neutrino astronomy channel is to use the planet as a filter. You look for things that are upgoing at the South Pole, which means that you're looking through the planet, which means that you're looking into the northern sky with neutrinos. And that's why this traditional channel results in the best sensitivity for IceCube in the northern sky. So in 2013, IceCube discovered an all-sky flux of neutrinos. And let me just show you one plot. There's more, but let me just show you one. This is in black data for neutrinos. These are the remaining 100,000 neutrinos per year. And then these line in purple that overlaps with the black at lower energy. See that you have energy here. And here you have flux in the vertical scale, or number of counts, I'm sorry, in the vertical scale. And these are atmospheric neutrinos. And these are the so-called conventional atmospheric neutrinos. Let me now explain the ones that are not conventional, because I will not have time. And then here in red, we have the astrophysical neutrinos. And you see that as you go to higher and higher energy, the probability that a given event is astrophysical goes up. And at roughly this energy, which is say 100 TeV, 200 TeV, then you have an event more likely being astrophysical than it is atmospheric. So the higher the energy of the event, the more likely it is to be atmospheric, to be astrophysical. And see that what we're measuring here is not the neutrino energy, but the energy of the muon that is deposited inside of the detector. Okay, so this observation was made initially in 2013. Since then, we have reported it with multiple methods, and we're absolutely certain that it is there. The spectrum is usually described as a power law in energy, and that power law has a spectral index, and the spectrum is relatively soft, and relatively soft I'll explain in just a minute, but the spectral index that we have right now is about 2.37. So let me put the neutrino observation in context again with other particles that we have observed. These here are observations using, again, several channels, and you have the 4 references there, by IceCube. And by being something soft or hard, I mean how steep this line is. This is the power law. If something is very steep, we say that that is very soft because you have few high energy events compared to low energy events. So it's very soft. You say something is very hard if you have a lot of high energy events compared to the low energy events. So this spectrum is relatively soft. It's not flat in this scale, in this way that I have shown to show it. I've multiplied here by e squared to make it flatter, but this is still, sloped down. These here are gamma rays observed by the Fermi-Lat satellite, the Fermi-Lat detector, and this is the all-sky isotropic flux of gamma rays, whereas our neutrinos are all-sky isotropic neutrinos. The fact that they're isotropic means that they're likely to be extragalactic in origin, both here and here, because distant galaxies are distributed more or less isotropically in the sky. Now, remember that when you have neutral pions, you can get photons, and when you have charged pions, you can get neutrinos. The only way to get neutrinos is via pions, but there are other ways to get photons besides pions. So the question is this flux related to this flux via pions? And the answer is probably no. And then it's again because this spectrum is very soft. If you take this and you extrapolate it to low energies, you see that you overshoot this. And that's a simplified calculation. If you want to, when we get to the question session, I can go to the more detailed explanation of this. But the fact that this sort of like shoots over and you extrapolate it to this set means that this set of neutrinos is not made by the same things that are making these high energy gamma rays. And that, in few words, is a very interesting observation. The sources of neutrinos have to be opaque to gamma rays, If they were not opaque to gamma rays, they were transparent to gamma rays, there should be a lot more gamma rays than what we actually see. And that is already in itself a very interesting observation. We do not know the origin of these high energy neutrinos because each one is resolved within half a degree, which is not enough to pinpoint any specific galaxy. However, we know that the sources are opaque to gamma rays. So in summary, for the extragalactic neutrinos, we know we have observed with multiple methods. We know it's isotropic, therefore probably extragalactic. There's no single class of objects that we have identified that we say, oh, that's a source. However, to date, we have 2 candidate neutrino sources, 2 individual candidate neutrino sources. One is called TXS, that was reported in 2018, and I will not have time to tell you about it today. However, today I will tell you about NGC 1068. This was reported last November. Both these objects are so-called active galaxies. In an active galaxy, you have a supermassive black hole at the center of the galaxy. All large galaxies have a supermassive black hole at their center that are millions or more in mass compared to the sun. However, these active galaxies, unlike in our own galaxy, are eating material. There's an accretion disk of material that is slowly feeding the black hole. And there are high energy processes that we suspect are responsible for producing neutrinos near these star sources. However, there are very different looking type of active galaxies. This TXS is a blazar, which means that it has a powerful jet that is pointing toward us. And the initial suspicion is that the neutrinos are being made in the jet. Whereas NGC 1068 is a Seyfert, and there's no powerful jet pointing toward us. So if there are neutrinos, they have to be made via a different mechanism. So now let me tell you about NGC 1068. So let's say that we want to look for neutrino point sources in the sky. So I already told you that you have 10 to the 11 muons per year and 10 to the 5 atmospheric neutrinos per year. So that means that if you plot your atmospheric neutrinos after you filter it, and see, this is the northern sky, this is so-called celestial or equatorial coordinates, you get a haze of neutrinos looking everywhere. And these neutrinos, if you look at them, they're more or less uniformly distributed, perhaps not in declination, which is this direction, but definitely this direction, which is the right ascension. If you take a region here and you zoom in, and this is how it will look like, and this is now all the events in 10 years or so, and see that there's no obvious clustering. And in this zoom in, what we have done is that we have artificially simulated, on top of real data, artificially simulated an astrophysical source of neutrinos. And you see that, again, each event typically has an uncertainty of half a degree, which means that some are going to be much closer than half a degree in uncertainty with the real direction, and some are going to be significantly farther away than the half a degree. So you get this clustering of events. But see that it is very hard by eye to tell that there's a neutrino cluster here. The only reason you know that there's a neutrino cluster here is because I've used a different color, to be really frank. So to identify neutrino sources, we're going to be using two pieces of information. One is direction. We look at a specific direction in the sky, and then we look at every single neutrino, and we say, how far away is it? And therefore, we can establish a probability, or a probability density function, to be exact, of that neutrino coming from that specific source. Neutrino that is really far is very unlikely to have come from a source here. Neutrino that is very close is a lot more likely to come from a source that is located here. But we're also going to be using the energy information, because remember that atmospheric neutrinos are very, 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 very soft. There are very few high energy neutrinos compared to low energy neutrinos, but astrophysical neutrinos are harder compared to atmospheric neutrinos. So the higher energy neutrino is, the more likely it is to be astrophysical. And those two pieces of information are going to look for to identify neutrino sources. We have conducted many searches for point sources in IceCube, doing this correlation of neutrinos in energy and in direction. And the prior most significant result had been NGC 1068 itself, that had a significance post-trials, everything taken into account, of 2.9 sigma. And we follow the particle physics convention of calling something that is 3 sigma or higher evidence and 5 sigma or higher discovery. So this was still not at the level that we would even call evidence for neutrino source. So since that publication in 2020, we have done multiple things. So first is that we have recalibrated and improved the data processing for IceCube. When we deployed IceCube in 2010, began operating in 2011, and then we have collected data in yearly campaigns. And every year we have done a small improvements to the calibration and to the data processing. And then when it comes time to analyze, the traditional way of doing it was to put all the data sets together and analyze it together, and that's it. But then now that we have used multiple years of data, we had gone back to the hard drives and reprocess all the data with the most modern methods and with the most up-to-date calibrations uniformly. And that has improved the sensitivity simply by going back to the older years and improving the better methods. This is known as IceCube Pass 2. And the calibration, the most important term in that calibration is to determine the light level that corresponds to 1 photoelectron. The calibration, I'm sorry, the electrical level that corresponds to 1 photoelectron in our sensors. You know, what is the voltage that corresponds to 1 photoelectron? That was tweaked a little bit, and that actually had a measurable effect in our ability to reconstruct neutrinos well. And this reprocessing was done to all 10 to the 12 events that we have calculated over the past 10 years. There's a significant computational effort. Then the other thing that we did was improve precisely these things, two things that I told you. See that we use the clustering in direction and the fact that neutrino sources are harder than background. We improve both these two things in our methods when searching for neutrino point sources. In particular, we describe the directional uncertainty better, and we have a better energy reconstruction. So let me begin with the better description of the angular uncertainty. So if I tell you this is the direction, the true direction, and here's a neutrino, how is that mistake, if you will, distributed? And the most naive interpretation that anybody would make is say, well, that's a two-dimensional Gaussian in the sky. You have 2D normal, and that has a width, and that width of that, or standard deviation, is going to be what we call the uncertainty on the event, and that'll be, say, half a degree or whatever. But actually, that two-dimensional normal function is not a very good, in some cases, description of how the uncertainty is actually distributed. Here you have two events. Both events are events that point in the direction of NGC 1068 and have a high probability of being from NGC 1068. And here you have our estimate of the uncertainty of that event, and then you also have the distribution simulated in orange and in blue of how the angular uncertainty looks like. And then you have the two functions in blue for the new analysis and orange for the old analysis on how that is approximated. So the orange is the 2D normal, and the blue is the new methods, which we just fit to the simulation using a method that is called KDEs. And you see that both do a reasonably good job of representing the data. However, when you move to the right, you see that the simulation in blue and the curve in blue match really well, but the model in orange and the simulation in orange are really poor description. So this 2D normal that we have been assuming in this specific event was a really bad description of what we actually have in our data. And this has consequences in terms of our sensitivity to identify these events. This is sort of like a really bad case, and this is sort of like a really good case. So that, typical events are going to be somewhere in between. We have also improved the energy reconstruction, and you see that with the old methods here, you have true energy. This is logarithm of energy. So this is 100 GeV, 10 TeV, 1 PeV. And here we have the logarithm of the reconstructed energy. And you want something that goes along the diagonal, the black line, and the median reconstruction is actually that white. So it does a really good job, but see that it has a bias at low energies. And the width here, is going to be the square root of the variance, okay? These are the new methods. And see that how the white line now doesn't have that bias at low energies anymore. See that we are able to reconstruct well to lower energies. And not only that, see how the standard square root of the variance is smaller here. So we have better precision and better accuracy for the muon energy reconstruction. And that is the other ingredient in our in the methods that we use to search for point sources. We have improved the calibration and processing, better description of how we say where a neutrino is coming from, and how much energy the neutrino, the muon due to the neutrino has. So all these things put together is this new sky map in the entire sky. And what this is plotting is the local probability that a specific direction corresponds to a specific to having a neutrino source. And all these little circles are a catalog that we pre-established. We used blind techniques, and that we pre-established as being potentially interesting neutrino sources. So before we began the analysis, we said these 110 sources look interesting. And these 110 sources, you have some sources that are galactic, some sources that are extragalactic. And among the extragalactic, you have various classes of objects. You have blazars, which is, one of the active type of galactic galaxies that I told you about. We also have so-called starburst galaxies, which are galaxies that produce a lot more new stars than, for example, our galaxy. And we have, large number of different objects here. If you look in the direction of these 110 specific objects, the most significant one is NGC 1068. And here is the zoom in of that map of p-values or probabilities. And this is the location of NGC 1068. And you see that, the location of 1068 is precisely on top of one of these hot spots. The reconstructed number of neutrinos that are coming from this point, from this specific direction, is about 80. Let's ignore the spectral index for now. There's about 80 neutrinos that are reconstructed in that direction. And once it took into account all the trials, because you're looking at multiple directions at the same time, the global significance is 4.2 sigma. So it means that we have now very clear evidence for a neutrino source. So let me spend a little bit of time talking about NGC 1068. It is an active galaxy. This is a picture taken by Hubble. And, here's the core where we have a supermassive black hole. And, this is a picture by Hubble. This, of course, this zoom in is, of course, an artist rendition. We cannot see this. But the idea of this black hole is that it is hiding behind a torus of material. This is an obscure black hole, which actually fits really well with the information that I had given you before, that the sources of the astrophysical neutrino flux are likely to be opaque to gamma rays. Because if you have neutrinos being produced very close to this black hole, neutrinos are able to escape because they can go through anything, no problem. If you have gamma rays that are produced near the black hole, they're going to be absorbed by these torus, absorbed and re-emitted at lower frequency or or larger wavelength. This is a view of how, again, drawing of how that region near the supermassive black hole could look like. You have the supermassive black hole, you have the accretion disk feeding the black hole, and there's very hot gas near the supermassive black hole. It forms like a corona. And we think that it is in this corona that is only, the size of this corona is only like 10 times the Schwarzschild radius of the black hole. We think that that's the region where the neutrinos are being produced. So what happens is that probably, this is what some theories say, you have strong magnetic fields here that are tied down by the accretion disk, and you get these magnetic fields get all tangled up. And when you get tangled up, you get a magnetic reconnection, and that produces particle acceleration. Then that, including protons, for example, these protons are going to interact with the strong X-rays that are present in this region, and the neutrinos are going to be produced via pions. So let me compare this NGC 1068 observation to other observations that we have made. So here I have energy squared times the flux. Here I have energy, and here is our best fit flux for NGC 1068. In gray here, you have the all sky flux. So you see that, this is 2 orders of magnitude. So it means that NGC 1068 is at most, say, 1% of the all sky flux. This flux here is the prior source that we had identified as a candidate, TXS, and see that it is also, again, maybe 1% of the all sky flux. But having these things put together, makes you reach some conclusions. One is that, well, we have 2 active galaxies. These active galaxies have very different observe electromagnetic properties, but there are 2 active galaxies. So it's a natural thing to speculate that active galaxies are probably contributing to a very large fraction of these overall extragalactic neutrino flux. Then the other is that, these 2 things, not only electromagnetic, but also neutrinos look very different. See that the spectrum, this is soft, this spectrum is hard. this source, we now know that we found that, you know, using this method that I do describe, but if you look at the timing information, this source looks more or less steady. However, this source, we identified it precisely because it is variable. There are two periods that are intense flaring in neutrinos, one in the end of 2014, beginning of 2015, and the other in 2017, when this source appears to have been active. So yes, we say that active galaxies are probably responsible for these neutrinos, but why do these two sources look so different? So, you know, those are some of the things that we want to find out. We don't have an answer for any of this. And NGC 1068 is opaque to gamma rays, and this one maybe at least sometimes is opaque to gamma rays, but it's not clear if that is true all the time. This result, as I mentioned, was published last November. It was published in the journal Science, and you know, this is just from the you know, pasting together the material from the article itself. Okay, so I will finish my presentation talking very briefly about a recent gamma ray burst, and these are gamma ray burst that is very interesting because it is unusually bright. So let me describe what gamma ray bursts are. Gamma ray bursts happen in very short bursts, naturally, of between 0.1 and 1,000 seconds, and they're very bright in MeV gamma rays, 10 to the 6 electron volt gamma rays. And there's a long history of models that lead to neutrino production, including here some references that result in neutrinos that are 10 GeV to 100 GeV. And, you know, 10 GeV to 100 GeV for IceCube is a bit on the low energy side. The NGC 1068 observations that I show you begin at a 1 tera-electron volt, so maybe a factor of 10 higher than this number. And, you know, here's a view of SWIFT, which is a detector sensitive to gamma ray burst. And you can see the brightest spot there correspond to the location of that specific GRB. And here's an artist rendition of a gamma ray burst. We think they always have jets, and we see the gamma ray burst when the jet is pointed toward us. There are two types of progenitors for gamma ray bursts we nowadays know. One is short gamma ray bursts that last less than 2 seconds, and they're the merger of compact objects like two neutron stars. So that will give rise also to gravitational waves that I'm sure you have heard about. And then you also have long bursts, which are associated with a subclass of core collapse supernovae. So these specific gamma ray bursts happened October of last year. And you know, here's a view of Fermi-Lat over 10 hours. These diagonal band that you see there, that is the Milky Way seen with gamma rays. And in gamma rays, just like in many other electromagnetic energy ranges, the Milky Way is typically the brightest thing that you have in the sky beyond the sun. And you see that this is the gamma ray burst, and you can see that it outshines our galaxy by significant factor as the gamma ray burst is happening. In fact, this gamma ray burst was so unusually bright that somebody calculated that this is a 1 in every 10,000 year sort of event. And yeah, so we have conducted with IceCube 5 studies, and I will describe you one specific result that was done by a PhD student of mine using DeepCore. And DeepCore is a sub-detector inside IceCube, and Sanjeev and other people over there work with DeepCore, and it's a group of strings and optical sensors that have been instrumented closer together. Because you put all these optical sensors closer together, you can see fainter chunk of light, and therefore you can see lower energy neutrinos. So whereas IceCube begins studying neutrinos at roughly 1 TeV or 10 to the 12 electron volts, with DeepCore you can begin at 10 GeV. You can begin at 10 GeV. So my student that Bennett this analysis, and this is a model in which you have the following situation. You have a jet coming out, and this jet is a little bit like the fireball, you know, after the Big Bang. If you have particles, all these particles are going to be coupled to each other via electromagnetic interactions or strong interactions or whatever. So for example, if you have protons and neutrons, they're coupled to each other via the strong force. and they're producing pions all the time, and they're re-interacting with each other all the time. As the fireball expands, then this becomes lower temperature, lower density, and then these protons and neutrons are able to decouple each other. They stream freely. The protons are charged, so they continue to be coupled to other charged particles in the ejecta of the jet. But the neutrons that are not electrically charged, they just coast. They're just free streaming. And these neutrons that are just free streaming are going to be hit from behind by other protons, and we have those collisions, neutrinos are produced. And here's an example for this specific GRB of a model for how many neutrinos we should be seeing. And these are limits that we have put as a function of several spectral indices on this GRB. And these in turns can be turned into a limit on how many protons and neutrons there are in the jet, that is quantified the so-called baryon loading. And the back of the envelope limit, we have not finished this calculation, is that the baryon loading is about a factor of 10 lower than theorists usually assume. So let me tell you then about coming back to this topic of the birth of high energy neutrino astrophysics, because I have to answer that. Are we really witnessing the birth of high energy neutrino astrophysics? So first we have an all sky extragalactic flux of neutrinos. Then we have two candidate sources. Both are about 1% of the all sky flux, and both are, we have clear evidence for having seen them. They're both active galaxies. They both may indicate that these two sources are opaque, which is more or less what we expect, but it's not still a complete picture. And do you judge this to be sufficient or not? In my opinion, yes. This is clearly a sign that we'll see the birth of high energy neutrino astronomy. So if you watch IceCube carefully over the next few years, you will see more and more results, as well as the strengthening in the result on NGC 1068, because NGC 1068, like I said, is probably the steady source. So it means that as years come on, we should be seeing more and more neutrinos from NGC 1068, and the significance of this source should be going up as time goes along. So the near future for IceCube is the so-called IceCube upgrade. This is a project that is already funded. We're going to deploy it in 2025, 2026, 7 new strings. And these strings are even closer together than those of deep core. And they're going to be used mostly for neutrino physics, neutrino oscillations. However, we're going to put the sensors so close together that we're going to be able to study the optical properties of the ice in regimes we have not been able to study them before. And that means that we should be able to understand the optical properties of the ice in ways that we cannot right now. And ice, being a natural medium again, is the largest source of uncertainty in our detector. If we understand the ice better, we should be able to recalibrate all the data, just like we did with PASS2, and improve the angular uncertainty for all events across all energies. Further into the future, we're thinking about IceCube Gen 2. And IceCube Gen 2 will have a volume that will be about 10 times that of IceCube. Here it is, drawing in artist mode, and it will have a sensitivity to point source that will be about 5 times better, and that should result in about 10 to 12 times more neutrino sources than we have in IceCube. So let me thank you very much for your attention, and let me describe this picture just a moment, because it is a really beautiful picture. This was done by Kunal. He got his PhD last year, and he included this picture in his PhD thesis. And you see here is the detector, IceCube, all the strings and all the sensors. Here's a muon passing through the detector, chunk of light from the muon. Each one of these is one of the 350 members of IceCube. And then here in the corners, you have neutrino sources, like an active galaxy with a jet, or the sun, etc. The moon doesn't make neutrinos, but it doesn't matter. This is so beautiful that it deserves, to be shown anyway. So thank you very much for your attention, and I'll be happy to take your questions.
Thank you, Ignacio, for this interesting talk. And it was so clear from very beginning. And indeed, this picture you showed earlier, and this is very beautiful, and it's made up of your student, your PhD student did this.
This picture, Kunal is not my PhD student. He got his PhD at Stockholm University in Sweden.
Okay. Okay, great. So now it's time to have questions. So if you have any questions, please raise your hand, or you can just speak. You just unmute and speak if you have any questions. Especially students, if you have any questions, just so are there any questions?
Hello, hi Sanjeev sir. I have a question.
So Ignacio, Ashish is speaking. He's a postdoc in our group.
Nice to meet
So
you.
yes, Ashish, please go ahead and ask your question.
Yeah, thank you, Professor Ignacio. It's a very nice talk. Can you go to your slide number 14, I think, yeah, where you were talking about extrapolation of the power law flux towards the lower end?
Yes.
Yeah, so you said that if we extrapolate it towards the lower end, we see that we should expect more gamma rays than we are seeing already. And the reason is that maybe these sources are opaque to these gamma rays, right?
Yes.
But isn't it against our hope to do multi-messenger astronomy with the high energy neutrinos along with gamma rays?
Yes. Yes. Well, I mean, multi-messenger astronomy doesn't have to be with gamma rays. So here's a more complete picture. So you see that you have neutrinos here. And if you have neutrinos, these are neutrinos presumably made by pions. So there should be about the same number of gamma rays, roughly this flux also there, approximately.
Right.
Okay. Now, as I said, the universe is opaque to gamma rays. So these gamma rays never get to Earth. Okay. However, if you have lower energy gamma rays, if the sources are opaque, these gamma rays are going to be reabsorbing the source and then be re-emitted at a lower frequency. So for example, you could have, say, GeV gamma rays, which would be 10 to the 9, that the source is opaque and they get re-emitted at, say, MeV. So you can still do multi-messenger astronomy, so that you have to know which is the wavelength of photons that you have to study. And we do not know that. You have tried many correlations between neutrinos and radio, neutrinos and infrared, neutrinos and optical, but we do not know exactly where is that we have to look. But the multi-messenger idea is definitely alive and kicking.
Okay, yeah, of course. So this scattering, this down scattering will be just like the Compton kind of scattering of these gamma rays. Yeah.
No, this will be E-pair production. So you have
Okay.
photon-photon collide, and in that collision, the invariant mass of the two photons is twice the mass of the electron or higher, so that an electron-positron pair can be produced.
Okay. Can you go just one slide back, 13? So while you were saying that at the higher energies, you are able to explain the data with power law flux, but this power law flux, for example, for the astrophysical, is not completely power law towards the lower end, right? I don't see the
so this spectrum.
Yeah.
So this spectrum is not the one that we describe with a power law. You see that this is the muon energy. This is not the neutrino energy. The neutrino energy is the one that we describe with a power law, which is what you have here. You see these bands here, these bow ties, are actually a power law, including their uncertainties. So a power law in log scale, so it looks like a straight line. So yes. In neutrino energy, this is a power law.
And it will still be sorry to interrupt, but it will still be a straight line, like for the whole energy range we are considering.
So we have relatively limited statistics, okay? And so you see here, you have in one of these bands, for example, for tracks, you have, say, 250, 350 neutrinos per year. So we have a relatively narrow energy range over which we're doing the observation. If there is curvature to this spectrum, which probably there is, we're not able to observe it with the current statistics. We have tried to do that. We have seen, can we fit this better with a log parabola spectrum? Can we assume that there's a break or some other combination, so a power law and exponential cutoff? We have tried several other things. We just don't have enough statistics to find deviation from the power law. But you do expect that it doesn't have to be a power law. There have to be cutoffs somewhere at a minimum.
Towards both ends or towards the higher end?
Probably both. Probably both.
Okay.
And we're limited on the statistics by both.
Okay. Yeah. Thank you very much.
Mm-hmm.
Yeah, Mohammed, you have question? Hi.
Hi. Thank you, Professor Ignacio, for the wonderful talk. Yes, I do have a question. So out of the 110 candidates in the catalog, why was NGC 1068 very special? Because like I see that it is a radio quiet, obscured AGN in a very small declination, right? Like near horizon.
Yeah. So the sources were initially, these 110 sources were initially selected using the Fermi-Lat information. And what we decided is that if you take the 110 brightest sources in Fermi-Lat, you end up with 110 blazars, very likely. But we wanted to consider several categories of objects. So we took a certain number of blazars, and we see that certain numbers that are, supernova remnants, a certain number that are pulsar wind nebula. Supernova remnants are pulsar in our galaxy, of course. But then extragalactic, we have several categories. And in the category that NGC 1068 is, it is the brightest in gamma rays. So it is not a bright source by any stretch of the imagination. Is that within its category, it ended up being among the brightest.
Okay, that makes sense. Thank you.
So, Ignacio, just to add to the Mohammed's question, do we have an age at this declination in IceCube that we found it early? Like, is it favored by any means in IceCube? Like this location?
So as I've said, our best sensitivities in the northern sky. We have some sensitivity in the southern sky that I have not described in this talk, but our best sensitivity is in the northern sky. If you look at the best sensitivity in the northern sky, it is precisely very close to declination 0 here, the equator in the sky, that our best sensitivity is. And the sensitivity here is a little bit worse. It's not dramatic, but it's a bit worse than it is here. So, I mean, is it luck or not that NGC 1068 is there? Maybe it's a combination of both. I'm not sure. When you only have one, it's really hard to answer that, right?
Right. So when you say sensitivity means basically you are focusing on the reconstruction of energy and the direction, right? That you have better. Yeah.
When I say sensitivity, I mean the ability to identify if there is a source there or not. That's what I mean by sensitivity. And that identification relies on energy and reconstruction of direction. But when I say sensitivity is, where is it easier to find the source? And is the easiest near the celestial equator.
I see. So, like we use like 80 events, we see a clustering of around like 80 events that you wrote in the slide. And we can confirm that we can really identify that they belong to this mother source, and the adjacent events are coming from different sources, and we can really separate because of the angular resolution. So how many total number of events we have seen, like 400, 500, like this is 80 events which corresponds to one particular source, but we have many events, right? In the northern sky.
So this is not in the direction of NGC 1068. You can tell that because this is like 30 degrees declination, so it's not in the equator, okay? But this number of gray spots corresponds to roughly how many you would have in these almost 9 years of data, okay?
These are astrophysical or these are atmospheric?
These
also?
are atmospheric. These are so overwhelmingly atmospheric. Overwhelmingly atmospheric. So you see, you have 100,000 neutrinos per year in the northern sky,
Right.
and then you know the northern sky is about 20,000 square degrees. So that means that you have roughly 5 atmospheric neutrinos per square degree per year. So if you multiply that by, say, 10 years of data, it's a bit less than that. But let's say 10 years, so you have 50 atmospheric neutrinos per square degree per year.
And we are interested in astrophysical neutrino events, right? So these are background. So I'm talking about like these 80 astrophysical events are corresponding to NGC 168. But
correct.
What is the total number that we have accumulated? Like that these are my astrophysical neutrino events so far.
Oh, I see what you mean. Over the entire sky.
Right. And in 10 years, maybe.
So it's what I said here. We have roughly 400 that we can identify statistically. We cannot say neutrino by neutrino, this is astrophysical, this is not. But statistically, we identify about 400 per year of being astrophysical. So you know, by 10 years, 4,000 or so.
So out of this 4,000, we could really separate these 80 odd events that they are coming from particular source, right? So
that's right.
Is that correct? So okay. So now
it's more complicated because you see that the energies are not the same. See here, see this gray band is the astrophysical of the sky, and this blue is the NGC 1068. And see that the energies ranges don't overlap. So we're seeing 80 events at a different energy range than the 4,000 events here, right? So this is not 80 out of these 4,000. 4,000 is 80 new events in addition to the 4,000.
Okay, got it.
I guess you can assume that this extrapolates or this extrapolate, but you have to make assumptions which maybe or not may or may not be correct.
Right. Okay. Are there any other questions, especially from students? Please feel free if you have any questions. Let me see any other hand.
Can I ask one more question?
Yes.
Yeah. So NGC 1068 is like you're not seeing the jet, but the blazar is like directly towards IceCube. I would have thought that like blazar being, you know, like a higher source of neutrino than NGC 1068. But in the flux region, you see like a discrepancy of that assumption. No?
So for a long time, it had been assumed that blazars would be a source of high energy neutrinos, and however, sources that are obscure, like NGC 1068, have also been assumed. The list of candidate neutrino sources, if you look at the past 30, 40 years of publication, the list of candidate sources is very, very long. So saying which is better theoretically motivated is really hard to answer. You can say, oh, this is really well motivated for pretty much every source that you can think of. And you know, these two sources, this source is very, very close. This source is, cosmologically speaking, really nearby. This is 14 megaparsecs away or so, okay? Whereas this source has a redshift of 0.33, and I forget how many megaparsecs that is, but it's pretty far. It's, oh, I forget the number, but it's a lot more than, it's a couple orders of magnitude farther away than NGC 1068. And so one question I have, if anything, is, you know, getting at the, you know, a really bright source being one of the first neutrino sources that we see be nearby, that sort of makes sense. How come is that we have something that is so far away and is still one of the first few sources that we see? This has to be amazingly powerful for us to be able to see it. This is, really bright in itself because it's among the firsts, but it's so close so that, okay, it makes sense. So, and then, the jet, again, that doesn't bother me, the presence or absence of jet, because there's models galore on neutrino source predictions. You can really pick and choose whatever you want.
Okay, thank you.
I think you're muted, Sanjeev.
Yeah. So you mentioned about these 110 different sources in the catalog. So it is really interesting that we have seen a nearby source which may have less intensity and a source which is far with very high intensity. And it seems like that the internal dynamics are also different. And with more statistics, we will probe better these two sources. But do you think that in that catalog, is there any other source like, we are really waiting for, like, or we have some best candidates from these two, discoveries, basically, because, each time we make a discovery, we learn more, right? That we have hopes, basically.
So for TXS, because we saw it flaring, then who knows if we're going to get more neutrinos or not. It could be another 15 years and we see no neutrinos, and that doesn't mean anything was wrong, right? It just it didn't flare again. So maybe we got lucky with TXS, and that was it with TXS. NGC 68, the data appears to be steady so far. So, and it's been, over 9 years, we saw 80 neutrinos, so it's about 9 neutrinos per year. So we should keep having about 9 neutrinos per year as time goes along. So if we add 5 more years of data, NGC 68, we should, measure the spectrum better, and the significance should, on average, still continue to go up. So we will definitely get better with NGC 68. As to additional sources, we do not have a single source right now that crosses the 3 sigma threshold. The closest one that I'm aware of is NGC 4151, that we have a recently finished analysis that was finished in last January, I forget exactly when, and we have already begun presenting in conferences, and the significance for that is 2.9. So it's a bit like NGC 68 in 2020. We're not going to call it evidence. We're going to stick by the 3 sigma rule. What's going to happen with NGC 4151? I don't know. I mean, we have to add more years of data to see it. If it's real, and I mean, if then in 4 years more of data or something like that, perhaps we should be able to see the significance go above 3 sigma. NGC 4151 is interesting because it is also an obscured source. The 2 sources that I talked about today, TXS and NGC 1068, are very, very different looking active galaxies. However, 1068 and 4151 are relatively similar. So it will be easier to understand 4151 if we believe, all is good with NGC 1068.
And this is also a very nearby AGN. This
4151 is, I think it's about the same distance as 1068.
Then makes sense. Makes sense. Yes. Okay, great. So let me see if there are other questions. I don't see, but feel free, if you have any question, you can write to us and I will convey this to Ignacio.
Thank you.
Ignacio, this is fascinating. Like some dream has come true, and like in 2013, like we were dreaming and now it's happening. And we can only say that all the best in this search, an exciting journey, and thanks a lot for for this precious time in over midnight, and you are talking us and telling us this exciting journey. We are really grateful, Ignacio, that you are making us learn. Thanks a lot, and we will have your video recorded, and with your permission we'll make it like public, and people can see and people can listen. And if we have any question, we'll pass it to you, Ignacio.
Thank you so much. And again, I'm very happy to have been here and being able to
Yeah,
talk to you.
it's our pleasure. These are the things that we learn from you, and we are excited, and I wish you all the best in this journey.
Thank you. Thank you.
Thank you, Ignacio.
Okay.
Ray, please take rest. It's too late for you, but thanks a lot again.
Okay. Goodbye.
Yeah, thank you.